All right, so let's take an example here. I want you're going to learn something really important about the nature of forces today. So if we've got something, I'm holding something in my hand, let's say I let it go. Okay. How many forces are active in that situation? If I let this thing go and it's falling. Okay, I'm hearing 2 and I'm hearing 1. Let's reconcile this. You said 2. Wait, what are they?
So there's gravity and there's the air resistance pushing.
Okay, let's say that for the sake of argument here, we're going to evacuate all the air out of the room. So then there's only one acting, right?
Yeah.
Make sense? That's true. There is only one force acting. And so what you're going to witness happening is exactly what you'd expect. This ball is going to fall down towards the center of the room. Okay? So let's change the situation a little bit. Let's take something like, let's take some exotic matter. So instead of anything, normal baryonic matter like you've got in here, we're going to take something like, let's maybe, how about if we take a cooled dwarf star. Okay, so if we take a cooled dwarf star, and which is, that's so after it's all cooled, and so what's going on there with the dwarf star? We'll talk. So we got a little fun intervening physics here, real quick. That'll just yeah. So let's talk a little stellar mechanics, real quick. This is kind of fun to do. So
White Knight.
So let's see. So in a star, there really are just 2 major large-scale forces acting in a star, right? That keeps it relatively constant in size. What do you think they are?
So gravitation.
So gravity, gravity is pulling all the matter in the star is being pulled by gravity towards its center, right? And then what's pushing out?
The vacuum of air.
No, vacuums don't pull.
Is that fusion or fission?
It's fusion, and it's the radiation pressure from all of the thermonuclear explosions that are happening in the center of the star, right? And so you've got this outward pressure that balances that, right? Does that make sense? Okay, so what happens then when a star runs out of fuel?
It blows.
Okay, two things generally happen, and we'll talk more about this some other time. We have a little more, kind of fun time. 2 things generally happen when the star runs out of fuel. Then what happens to the radiation pressure? It goes down. It goes down. So it goes out of balance, right? The radius of the star, which is predicted by the sum of these forces, becomes unbalanced, and the star starts to collapse. As the star starts to collapse, what happens to the furnace in the center of the star when all of a sudden you get this inrush of fuel, hydrogen fuel? Yeah, so for a very brief time, it's going to burn really, really hot, right? And so that's what can cause like a red giant star. Okay, so that's what happened to our sun. Our sun will turn into a red giant and get really big for a while, and then it's going to collapse all at once, and then probably be some kind of nova, right? So it's gonna burn really brightly, or not really brightly, but it's gonna burn with a lot of intensity, which is gonna push the star outwards. But when it finally does collapse, and all that hydrogen gets shoved into the center, it burns very, very brightly and very, very hotly, and that's what can cause a supernova, right? So that it explodes, and some percentage of the star's mass, say 12%, 10, 12%, gets ejected into space, and the rest of it just gets sucked back gravitationally. By the way, what's kind of interesting about this, I don't know if you probably maybe heard this in documentaries and things, but that intense fusion reaction that occurs, and we'll talk more about this when we talk about nuclear physics. We'll just talk about it for a couple weeks at some point. It burns so hot, and there's such active fusion going on in the center of the star that it doesn't just fuse hydrogen to form helium. It actually fuses hydrogen to form heavier elements, right? Enough energy is invested that you can actually create heavier elements like iron and nickel and things like that. And so all the carbon, all this stuff everywhere in the room that's not hydrogen, which is about 99.99% of it right here in this room, on our rocky planet. I just calculated that. All this stuff is actually the ejecta from a star. That's all this stuff, everything that you're made of, honestly, is you are. You came from the innards of a star when it went supernova.
So
That's the only place that those heavy materials ever get created. They don't get created, did not get created early in the universe. In the Big Bang was just, all that is just hydrogen expanded, right? That's what the universe was predominantly originally, was just hydrogen. It's only in these little pockets of gravitational collapse where you get supernova occurring that you actually ever get any heavier elements. And so they get dispersed throughout in our case, get dispersed throughout the galaxy. And then all that dust, over time, it accumulates. And, you get rocky planets like ours, which is just a slow accumulation of all this stuff that got spit out of a star. And that's where we are. That's who we are. We're star stuff, yeah.
So might we see space mining in the future? Do you know what I mean?
Well, space mining, it's a realistic question in a way, because like if you wanted to get lots and lots of iron and nickel, where you would probably want to go is to an asteroid.
Right.
Yeah, so if you had the technology
Right.
and it was cost effective in terms of fuel, to get to an asteroid, you could theoretically gravitationally harness an asteroid and mine it and get the raw materials. If you wanted to build something like a very large scale spaceship in our distant future, if we want to travel to other
That's
stars,
what I'm talking
that's where you're going to have
about.
to get the
When we're
raw
living in
materials.
space.
You can't lift them off the surface of a planet because it takes too much energy to get them away from the planet, right? Yeah.
So, did we become a planet and then just get picked up by our sun and its gravitation?
No. It really, in a nutshell, very briefly, the development of our solar system, it would have originally been just like a big spiraling cloud of stuff, of ice and hydrogen, mostly hydrogen, but then a little bit of rocky material, stuff that would eventually become rocky material, stuff that was not gaseous, that was solid, that was heavier. And so that stuff accumulates into rocks, accumulates into ice, and then those things swim into each other, and eventually they start to build bigger and bigger pieces of rocky material. And so, if you looked like our solar system viewed from above, so to speak, so looking perpendicular to the plane of the orbits of the planets, would just look kind of like this. So you'd have the sun is in the center, and let's just take Earth for example. So here's Earth's orbit around the sun. Well, Earth is just a rocky planet that just kind of gathered up all the crap that was sort of in this area, right? And that all came together and formed a rocky planet, and that's us.
So why, when we got bigger, didn't we get closer to the sun?
We probably did a little bit. Probably did. Yeah. As it collected, but this thing was spinning also is the thing. All this stuff was, whenever you watch stuff infall, it's always, the mechanics, for reasons I'm not going to explain right now. When you watch stuff infall, even in a volume, in a three-dimensional volume, energy is, the most energetically stable state is for that stuff to fall into a disk of accretion, right? So it's going to always, galaxies are always, they look like flat, right? Once stuff has fallen in for a while. And so all this stuff is spinning. And so the relative velocities between the Earth and the little particles that are around it, they're all going the same direction, right? You get a few of them that are just a little bit faster, they get pulled in, and a few of them, they get pulled backwards a little bit. But it's not really affecting, it's not like it's plummeting around through space and picking up the stationary material. It's essentially rotating with it anyway, right? Okay. Does that make sense? Okay. And then most of the water actually on our planet would have come from infalling comets. When there's during the period of cosmic bombardment or of comet bombardment, there was a period where the solar system was littered with comets, and they would have all been gravitationally, well, not all, but many of them would have been gravitationally pulled in, and the water from those comets would have seeded our planet with water, the ice from the comets, and then they would have had lots of long chain amino acids and things, and so it's all kinds of good, potentially biologic material comes out of that as well. But I digress. So anyway, back to our back to our discussion of the star here, right? So how did I get off? Oh, with the heavy, that's right. I gotta retrace the steps here sometime. So when all this stuff infalls and it's ejected, a lot of it's ejected, most of it remains. And then it continues to infall, and as the furnace cools and cools and cools, there no longer is any of this radiation pressure pushing out on the material in the star. And so it gets sucked in. Well, what happens? Well, okay, depends. Depends on the mass of the star. If the star is smaller, actually even like ours will not become a black hole. It's not big enough. There's not enough mass. But as it gets sucked in closer and closer, well, all that mass is still concentrated at the same point, right? And at some point, the mass is crunched in. I gotta maybe do one more thing for you. If we were to burrow through our planet, so here's our planet. This is gonna be one of our projects that we're gonna do in physics. We're going to create a tunnel that goes all the way through to the center of the Earth, which we're gonna hollow out. We're gonna create, the very center, we're gonna create a little, let's say a 10-meter sphere that's just empty, right? And we'll be able to go down to that. We're gonna have to line it with pretty good insulators there. It gets kind of hot down there, but what do you think would happen if you were to climb down that ladder?
Well, you get incinerated.
Okay, when you get to the center, gravity would probably just be huge, right? Make sense? That's not what happens. As you get to the center, when you get to the very center of the planet in here, and you're floating around in that little disk in the center, or that little sphere in the center, that hollowed out area, there would be no gravity. You'd be able to just float around and push off from one wall to the other. It'd be kind of fun.
Right next to it.
There would be, okay, here's the thing. Only if you do the calculus, which you'll do when you take calculus-based physics, maybe in college, not first class, but after you go through a few, you'll do these kinds of things, and you'll calculate what the gravitational field is by summing up the contributions of all the particles in the planet, which you can do with three-dimensional calculus. And when you do that, what you find is that the only part of the Earth that contributes gravitationally to the gravitational field is the part that is lower than you are, right? So for us, that's the whole Earth, because we're all standing at one radius away from the center of the Earth, right? Roughly 6 million meters. And there's 6 million meters deep worth of Earth that's spherical, right? So when we walk around the surface, we're always walking around the outside of all that. Does that make sense when I say outside?
So the closer you get, the less gravity there is.
Exactly. So when I climb down this little ladder here, I'm going to get to a point. Let's say when I go halfway. When I go halfway down the ladder, then only the portion of the Earth, the kind of that subsphere of the Earth that is closer to the center than I am, is going to gravitationally contribute to the gravity that I feel. Everything out, here's the weird part, everything above me, so the shell of Earth that is further away from the center than I am, that entire shell is going to contribute nothing. All of the gravitational field generated by each little particle of Earth above me is all going to perfectly cancel. And so which is weird, right? And so as you get closer and closer to the center, what you actually find is that you feel lighter as you get closer to the center, right? So in this, questions about that?
How is our planet stable?
Uh,
Is it unstable in the center and then just the outside
No,
is holding it all together?
It's stable because it's
I mean, obviously
it's
stable,
solid,
but-
right? I mean, and the interior it's malleable enough that what happens to the really dense material in our Earth? Where does it end up?
In the surface.
The center, right? The Earth has an iron core where all the really heavy stuff, sinks to the center, and then there's just some little tiny, just dusting of iron that gets brought up when there's volcanic activity and things. But all the iron we think of, lots of steel, you look around cars and buildings. I mean, think about that compared to the tremendous volume of iron that's sitting in the core. It's a fraction of a fraction of a fraction of a fraction of a percent, right? It's all really down there. And so it is stable for that reason, right? So this star, you'd think as you get closer and closer to the center of the star, the same kind of thing is going to happen, but not in this case because the star is being compressed, right? And so as the star is compressed, the inside of the star is moving in also, right? So all that mass is being concentrated into a smaller and smaller area. Well, what stops it, right? What stops it? There's two things that stop it. For one thing, one of them is called electron degeneracy pressure. So normal matter like this, I know you've seen stuff like this before. If when you knock on something like this, baryonic matter, it's mostly empty space, right? You've probably heard the model that if you were to take an atom, like say a hydrogen atom, and you were to blow it up so that the nucleus was the size of a golf ball, how big would the atom be?
Stadium.
It's huge. I mean, it'd be like several football fields, right? So it's mostly just empty space. And that empty space is there because in quantum mechanics, what we find is that the electrons, which have very, very small masses and very, very high speeds, need lots of elbow room. It's called degeneracy. Electron degeneracy pressure then is the fact that they need all this elbow room to stay contained in this little space means they push hard against the other atoms, and that's what creates, this mostly empty space, right? But you can crunch that down. If the gravitational field gets strong enough, you can take the matter and you can actually push down the electrons so that they sit much, much closer to each other than they normally would, and you're effectively like crushing the matter down closer than it wants to be, right? And that's when that happens, you get exotic matter that's much, much denser than anything you'd ordinarily see. So unlike a dwarf star, ours will collapse into a dwarf star. When that happens, the density is going to go up tremendously. You'd have something like, let's say, the size of a softball would have the mass of like a dump truck or something, right? So it'd be really, really, really dense. Okay, but you can go further than that. If the star gets a little bigger than that, if it gets something like, 2.3 or 3.1, I don't remember what the number is. If it gets somewhat larger than our sun, it will turn into what's called a neutron star. In a neutron star, it literally pushes the electrons down onto the surface of the protons, and nothing is left but neutrons, right? And so in that case, it's actually you're overcoming the nucleon degeneracy pressure that, the nucleons need all this, well actually hang on a second, just the electron degeneracy pressure. You're pushing the electrons down onto the protons, and effectively to make this really simplified, the negative and the positive charges cancel and you end up with neutrons only, right? So that makes it much, much denser. In that case, something with the size of like a basketball would have the mass of a mountain range or something, right? So you get really, really extremely exotic matter. And then if you go beyond that even, the neutron degeneracy pressure, the neutron's ability to maintain some elbow room, and they're much more tightly packed and much higher pressures, then eventually you kick over the threshold where there's nothing to stop it from collapsing anymore. There's no more forces to balance gravity out, and then what happens? Black hole, yeah. Then you get a black hole where you just get uncontained gravitational collapse, and eventually you just form a little hole in the universe, a black hole. So, then we'll talk more about that later. But why did I bring this whole thing up? This was a very circuitous path. But now let's say something else. Let's say that we've got now, instead of a basketball that I'm just dropping towards the ground, let's say that I've got some extremely exotic matter that's got roughly the mass of, say, half of the Earth that I'm dropping. What's that going to do when I drop that? First of all, I could never hold it, but let's just say magically I'm going to snap my fingers and it's going to appear. What's going to happen?
Go through the ground.
It's going to go right through the ground like it's not there. Yeah. But you're going to feel something.
You probably not even see it.
It would fall. Okay, the rate at which it would fall, coincidentally, would be not real different from when I drop the basketball.
It just keeps going.
But what's going to happen is, it's going to keep going, and it's just going to kind of riddle the core like Swiss cheese. It's going to go through the core out. If it were dropped from a height of, say, 6 meters, then someplace down in China or wherever the other side is going to be, it's going to pop out of the earth, and maybe slightly less, but not much, not measurably, because the friction is going to be so minimal compared to the force is acting here, it's gonna go back down again, go right through, back and forth,
So we
and
should
back
play
and
catch
forth.
with some people.
And we would want to sit here though, 'cause if we were sitting here, the gravitational forces would, we just get, you would just get kind of, you'd be like a layer of goo on the outside of the sphere when it heads down through, because the gravity would be so strong. But just pretend we were a ways away. You would feel something else happen though. Even if you didn't know this was going on, you didn't see me drop this thing. If you were, thousands of miles away in a safe distance, what would you feel?
Earthquake?
Well, okay, you would,
You just feel like,
Or would you feel kind of like a,
Like you
like
feel
a
like a
pressure?
hit.
no, you would feel something really, really
oh,
significant.
would it pull you, like it would pull you?
No,
Or would it be
Now
like
think
a
about
wind?
that. no. What would happen to the earth you were standing on?
It kind of shifts.
It would be
Because you
half
kinda
a
hold
mass.
And so if it had half the mass of the earth, then the earth is gonna be pretty significantly pulled towards it also, right? The point I'm making here is that the force that's acting on the object when it falls is not exclusively acting on the object. When I drop the ball, it's not just acting on the ball. Here, close your eyes and concentrate real hard. You ready? I'm gonna drop it right now. Did you feel it?
Yep.
You feel the earth rush up to meet the ball?
Yeah.
Okay. If this were the mass of the earth, you would have, right? If this were the mass of the earth would have gone rushing in that direction until the centers of mass were at the same place, and then it would have started to decelerate again. So you'd feel real heavy, the earth would be accelerating upward, and at the top, so it'd be weird, right?
Yeah.
Okay, we don't feel that only because the differences in mass are so dramatic, but if they were closer together, the centers of mass would just be doing this. One of these represents the earth, and one of these represents the object that I dropped. It would just keep going back and forth like this, the whole earth would, right?
Right, get smaller and smaller each time, just a little bit.
A little bit smaller each time, yeah.
So if you were, like,
Wow.
if that ball with the mass of the earth was going this way and you were standing on this side of the earth, would you just feel the earth go like left and right to you?
Yeah, so you'd be, right, so you'd be accelerated, you'd be falling, tripping to this direction for a long time, and then you'd stop and it'd pull you, you'd go sliding back that way across the planet.
I'd be messed up. I'll just lay down. You know, you're just like.
Okay, so what this long story is really telling us is this. It's telling us that for every action force, there exists an equal and opposite reaction force. That's Newton's third law. That's the way you've probably heard it if you've heard it before. Forces do not occur in isolation. Forces always occur in pairs, right? A force is shared by objects, right? So another way of thinking about that, a better way of saying it is this. Forces occur in action-reaction pairs that act on different objects, are equal in magnitude, and are opposite in direction. Every time, that's what happens. So if we're going to label an action force, let's say, as F, the force of A acting on B, then the reaction force is negative B on the same force acting B on A. So for example, if the action force is Earth pulls on ball, then what's the reaction force?
Ball pulls on Earth.
Ball pulls on Earth. And if the Earth is pulling on the ball in that direction, which is obvious if I drop it, whoops, in what direction is the ball pulling on the Earth? That direction, right? The forces are equal in magnitude. In this case, the accelerations are vastly different because the masses are so different. But the same force is acting on both the planet and the ball, okay? So what's a little bit tricky about this, not so tricky, but what's a little bit tricky is being able to identify the difference between external forces acting on a system and action-reaction pair forces acting within a system. Okay, so, okay.
Wait, so by equal magnitude.
So let's just say if the weight of the ball is 50 newtons that I'm dropping, what's the gravitational force acting on the ball? Okay, what's the gravitational force acting on the planet? 50 newtons. 50 newtons doesn't do much to a planet that's got a mass of 5.98 times 10 to the 24 kilograms. Okay. So let's look at this slide then. So if force is F, A on B, and the force B on A are action-reaction forces, neither causes the other, right? It's really kind of misleading in a way to say that one is an action force and one is a reaction force, because that almost implies that one of them happens and then the other one says, okay, I better act in response, right? Of course they act simultaneously, and it's completely arbitrary which one you call action and which one you call reaction, right? Usually the action force is the one that's most significant within the context of a situation. So if I drop a ball, then we're usually going to be more interested in the force acting on, earth on ball, right? But, that's what we would normally call the action force, but it doesn't have to be. We could just as easily say the action force is the ball pulling on the earth and the reaction force is the earth pulling on the ball. Makes no difference, right? They go together, in fact. Forces cannot occur in isolation. They have to occur in pairs between objects. A force in isolation would be like the sound of one hand clapping. It just doesn't make sense, right? You can't do it.
Actually, Nick can clap one hand.
Okay, all right. There's always one wise guy. So then, what's the difference between this slide up here on the upper left and this slide down here?
More than one external.
Okay, so what are external forces then? Let's take an example. Like if you are, for example, let's say you're in a car and you're playing catch with somebody across the back seat of the car. When you throw the ball to your neighbor across the seat, there's a pair of forces acting between what? When I throw the ball? Between me and the ball, exactly. I push on the ball and the ball pushes back on me, right? If it's a truck with a bench seat that's been armor-alled really well, and I'm wearing silk pants instead, so I'm real slippery. If I throw this thing hard enough, I'm going to recoil a little bit and slide across the bench seat, right? Everybody agree? And when the ball's going to I'm going to throw the ball this way, and then when the person catches it, they're going to slide a little bit if it's really armor-alled up, right? Okay. So those would be examples of internal forces, right? If you're outside the truck, you don't notice anything going on when they throw the ball back and forth inside the truck, right? It looks like a normal truck to you, right? Everything is internal to that system. But if the person slams on the brakes, the truck's going to come to a halt because then there's a frictional force that's acting outside of the system of the truck. And so that's an external force, right? Does that make sense? You can always define a system that's going to include that force internally, but you have to change the system, right? What would the system have to become if you want to now include that braking force on the truck as an internal force? From what perspective would you not notice anything weird happening? Okay, so maybe the truck plus the road, right? From the perspective, like if the car went through a tunnel and put on the brakes, you wouldn't notice anything, right? Does that make sense? Because then the forces are acting internally. That's a bad example because let's say that what happened was the car went through the tunnel and it collided with another car. Okay, so now that system is the two cars, not the road, right? Because you're attached to the road if you're outside the tunnel. See, that was a bad example. But so now that would be internal to the system of the two cars, and you wouldn't notice anything regardless of how sensitive your seismic instruments were, right? Because that collision happened between those two cars and didn't involve the earth, right? Does that make sense? Okay. If you wanted to include just the road, like friction with the road, you'd actually have to probably include the whole planet, right? Because technically, if we all started on the starting line here and we all sprinted that direction, we would roll the earth a little bit backwards with us, right? Because we're pushing on the earth, go forward, and the earth is pushing on us.
Wait, so is that why when people like go back in time and make the world go back in time?
Ooh, every time that happens so frequently? Yes.
Yeah.
Like Superman, no, there's not a lot of good physics going on in Superman.
So is
Yeah.
for the two cars hitting each other, why would we need the tunnel?
Well, you wouldn't, but if you couldn't see it happening, you would have no,
Oh, okay.
you couldn't measure any difference in the rotation of the earth, there's nothing you could ever measure that, right? Okay. All right, so then you could have things like this too, right? You could have things like, let's say that we've got system one is the truck where the people are playing catch with the ball, and system two is another car where people are playing catch with the ball. Those are two systems in their own, right? If they crash into each other, from the perspective of system one, that's an external force. From the perspective of system two, that's an internal force. But from the perspective of,
External and
oh, did I say it backwards? External.
You said both.
Oh, okay. I think I was not being careful what I was saying there. So from the perspective of system one, that crash force pushing on the car is external. From the perspective of system two, car two, it's going to be external. But if I take the combined system, system one and system two contained in a bigger system, it's internal, right? Make sense?
Yeah.
Okay, but from the perspective of that entire system, the gravitation, the weight of the cars would still be external, right? Because they're still being mysteriously pulled down into the road, right, by gravity. So we'd have to include the whole planet then, make the system even bigger to incorporate gravity also, right?
To make that whole thing.
Right. I mean, you have to just get you a pretty big system. Okay, questions on that? All right. So what about this guy then? See if this makes sense. Catching a ball here. So we've got two things we're looking at. We're going to look at the forces acting on the ball and the forces acting on the hand. So the forces acting on the ball, the weight is pushing down, right? So that's a vertical force pushing down on the ball. When the ball is caught, there's also going to be a force. The ball stops, right? So it's accelerated in that direction by the mitt too, right? So the hand is going to push in that direction. So do those two forces make sense then? Right? I guess I've got this maybe backwards, so I should be standing in this direction, right? The ball's coming in like this. I'm pushing on it in that direction and gravity's pushing on it down. So those are the two forces acting on the ball. What about the forces acting on the hand? Okay, on the hand, there's my hand. You got the ball pushing it that direction, right? Transferring, there's a force there. The weight of the hand is pulling it down towards the planet, but probably there's going to be maybe some other force acting where, like I said, I'm standing over here and I'm pushing up like this with my arm, and so my arm is also pushing on the hand at some angle, right? Of those forces, which of all those forces described there constitute an action-reaction pair?
The hand on the ball,
Yeah. Of the 5 forces there, the only 2 that are part of an action-reaction pair are going to be these 2, right? This force and that force, right? They meet all the criteria. Hand on ball, ball on hand. Equal magnitude, opposite direction, right? Does that make sense? Everything else is external, right? Okay. How about this car? Pretty simple situation. It wants to accelerate to the right. How much time we got? 4 minutes. It's not very much. I want to save this one for tomorrow because I don't want to get interrupted on this one.